This presentation is called Humpty Dumpty and His Wall, and what it's trying to introduce you to the idea of impulse momentum theory. And impulse momentum theory is it's really important in terms of your everyday life, in terms of keeping you safe in a traffic some sort of accident, or while you follow through whenever you're playing sports and those sorts of things. So great things are not done by impulse, but by a series of small things brought together. And that's a quote by George Eliot. So we want to look at the learning goals for this particular one, and it says you should be able to understand the factors that affect impulse. Okay, so you should know what impulse is, and then you should be able to say, okay, based on the factors that affect this impulse, what can I do with it? Can I design some sort of safety device in order to keep something safe? And you should be able to use the equation right here. This right here is the J equals F delta T equals M delta V. And people get kind of confused with that because it has these two equal signs right here. But you can think of it as two formulas. Or actually three. You can think of it as J equals F delta T. You can think of it as F delta T equals M delta V. And then finally you could think of it as J equals M delta V. They're kind of all equal to each other, so they just set it as one long equation. So we want to start off by looking at Newton's second law, and we want to expand it out a little bit. So Newton's second law, he originally wrote these in terms of momentum, not in terms of force. So he didn't come up with force and say, oh, look, I'm going to name it after myself. He didn't do that. He actually wrote it in terms of momentum. So you can actually combine these equations to get Newton's original version that he had. And if you see, it says F net equals ma and P equals mv. So if we were to look at this, V and P and M, there's a lot of similarities that go on here. So what we want to be able to do is we want to say just something a little bit different. If you were to look at F net equals M A. Now remember, A is actually the change in velocity over the change in time. That's the definition of acceleration. So if you were to look at this, you can now say, okay, I've got something that's going on here, and I'm getting pretty close to this idea right here of MV. But I need to move this t over to the other side in order to make that work. And so what you do is you multiply both sides by delta t, and you come up with the equation F delta t equals, and then you have m delta v. Now this term right here is how he actually wrote this equation. You have this idea that the change in an object's momentum is equal to the force times the time that's actually there. And this is actually how Newton wrote his particular equation. There's some disagreement of whether he left the time over here as far as divided by, or he'd moved it over, but he had actually written it with no acceleration at all in this particular equation. Now, in the egg toss, which you guys did earlier, it said what factors did you do to reduce the impact force on the eggs? And so there's a couple of things that you could have done. Generally speaking, whenever you toss the egg, whoever catches it with their hand and then brings their hand backwards. Now, if you were to leave your hand rigid and just catch it, it will shatter and it will break right there. Okay, that's the most important thing. Other people, what they try to do is they try and slow the egg down as much as possible. So just barely throw it till it can really just hardly ever get there. So really you can reduce the velocity of the egg whenever it hits, or you can do what's called increasing the impact time. So in other words, you're kind of slowing it down very gradually, or your acceleration is very small. If you have something that's really rigid, it won't actually work. And other people try to use things like cushions and things like that. But there's lots of things that you can do to reduce the impact force on the egg. And those are right here. The higher the velocity was, the more likely the egg was to break. So when you first started right next to each other, it was pretty easy to get it back and forth. But as the distance increased between the two, you had to throw it with a greater velocity to get it to actually go there. Well, when you throw it with a greater velocity, that velocity has to go away. You've got to bring it back to rest. And as a result, the higher the velocity, the more likely the egg was to break. Another factor that you really couldn't control in this particular lab was that the higher the mass, the more likely it was to break. So if I were to give you a jumbo egg with a greater mass of something like 90 grams, it is much more likely to break than a medium egg, which is somewhere around 50 grams, just because of its sheer mass. Second, or third, the more rigid your hand, the more likely it was to break. Not break, but to break. The more rigid your hand was. So like whenever you caught it, your hand should have given a little bit and kind of swung back. And that makes it much less likely that you'll break the egg. Well, this is very, very similar to what we talk about in terms of car safety. Okay, in terms of car safety, the anti-lock brakes help you reduce the car's velocity. So it used to be that your brakes would, if you slammed on the brakes, they would lock up and they just wouldn't work anymore. Okay, and because of that, they wouldn't work effectively and your car speed would be much greater. Well, by putting in anti-lock brakes, what it allows you to do is it allows you to keep braking, and so you can reduce the impact time. Okay, just like we said, we're trying to reduce the velocity of the egg, we're trying to reduce the velocity of the car before some sort of impact. Okay, next what we did is we said, okay, we want to be able to reduce the mass. And that's one of the other things we did is we construct the cars out of synthetic materials. Okay, you'll hear a lot of times that cars are made of plastic now, and people say that it's kind of a derogatory thing. They're not made out of iron and steel like they used to. There's a couple of different reasons why though, but yes, they are trying to reduce the mass. Couple of reasons is they're trying to keep you safer while you're actually in your car, and the second thing is it actually really helps out with gas mileage. If you think about it in terms of energy, which we just finished, okay, the less mass that's required, okay, the lower the mass, the lower the kinetic energy that you can have. Okay, next you have, and finally you have what are called crumple zones. The crumple zones are the idea of rigidity. Okay, the more rigid your hand is, the more likely it was to break. The more rigid your car is, okay, if it's made out of metal and it's really solid, the more likely it is to break. The impulse momentum theory is also useful when you're trying to increase the force on an object, not just decrease. So if you look earlier, we were trying to say, okay, how can I decrease the force on a person? Well, now I want to increase the force that's exerted on a ball. And so these are some things that generally coaches tell you to do. They say, okay, make sure that when you swing as hard as you can. So you're increasing the force that's exerted on the ball. That's kind of an easy one when you're trying to hit a home run, you swing hard. But whenever you look at this, you can also say increase the contact time. Remember, we wanted to decrease the contact time in our collision because we wanted to decrease the force. But if I want to increase the contact time, what that is following through. Okay? Now specifically it says use a metal bat because the metal bat will impart, it's more rigid and so it will impart more of a force in a shorter amount of time. But really what you want to do is you want to increase the contact time as much as you can. In this particular case, you can't change the mass. You're not allowed to say, okay, well, I'm going to switch a baseball to a softball or something like that. You can't do that. And actually increasing the mass wouldn't be very effective if you're trying to change the momentum or change the velocity of the ball. So you're not allowed to change the mass, so that's not an option for us. But if you swing hard and you follow through, that will impact the velocity of the ball. So in the first example it says the 8-ball and a ping pong ball are dropped from the height onto a force plate shown below. Which one do you expect to show the greatest change in momentum? Now this is kind of it's a conceptual question, but you could always back it up with math. So if you were to look at this, they're dropped from the same height. So if the height is equal, then you could use conservation of energy. You could say, well, GPE equals MGH. Here, right before it hits the plate, it would have kinetic energy, which is 1/2 mv squared. And you can cancel out and say, well, mass isn't going to matter when I calculate the velocity. And it's not. Okay, the mass is not going to matter whenever the velocity of the ball is determined. Both balls will have a certain initial velocity, which is whatever it is depending on their height, but that velocity is going to be the same there. Both balls are going to have some velocity and they're going to come to a rest. Okay, we're going to assume they're going to come to a rest. You could always have one bounce or something like that, but we're going to assume that they come to a rest. If they come to a rest, the change in velocity for both of these is going to be the same. So if you were to look at this particular, in this particular case, which one is going to show the greatest change in momentum? Well, remember, momentum means mass times velocity. I can really change two things. I can change the mass, or I can change the velocity to change the momentum. Now, I'm not changing the mass in these particular cases. Okay, the mass is going to stay constant throughout. This one is going to have a certain mass. This one is going to have a certain mass. Okay. The change in velocity, they're both going to be going from a certain velocity to 0. So a lot of people say, well, since there's no change in mass and the change in velocity is the same, they're going to have the same change in momentum, and that's not the case. Okay, you can say that the change in momentum is equal to the mass times the change in velocity. So for the 8-ball, it's going to have a larger mass. It's going to have a larger mass than the ping pong ball. So because of its larger mass, it's going to have a greater change in momentum, even though it has the same mass all the way throughout and the velocity change is the same. Next, it says, why are boxers taught to roll with the punch? It's one of those things where if you look, what we've talked about so far is if this guy is punching this guy, when he exerts a force right here, if you can increase that contact time, okay, remember he's going to get hit with a certain force anyway. So if you can kind of increase that contact time, what you're doing is you're decreasing the force because you're going to have the same change in momentum regardless. Okay, the mass of his head is constant. The change in velocity is going to be the same regardless. So it's like an airbag sort of situation where you have a set change in velocity, you have a set mass, so really the only thing you can do to decrease the force is increase the contact time. So if you kind of roll with the punch, which means he's kind of going backwards as he's being hit, this time drastically increases. When you increase the time, you decrease the force or the effectiveness of the punch. Kind of the opposite is you tend to see, if you've ever seen a boxing match where somebody's knocked out in one hit, what happens is they tend to be kind of leaning forward or going forward as they get hit, and that really shrinks the contact time and it really increases the force. So that's why they're taught to kind of go with the punch as opposed to trying to kind of step into it. And this example says, why should you follow through in golf to maximize your distance when striking the ball? Well, this is exactly like we had with the baseball. So there's no set change in velocity. What I really want to do is I want to change the momentum of this golf ball a lot. I want to get it to go this way. So I really, really want to change the momentum. Now, the mass of the golf ball is set. You can't change that, but you can change the velocity. So what we really want to do is we want to change the velocity. Well, how do we do that? Well, the first thing that you can do is you can swing hard. And I know that doesn't always work in golf because when you swing hard, you miss the sweet spot and all that kind of stuff. But for our purposes, what we're going to say is the harder you swing, the more force you're applying on the ball, the greater acceleration it's going to have, and then the more it's going to change velocity. So we're going to say that when you increase the force, you increase the change in velocity. The second thing that you can do is you can increase the time the force is applied. So if you can increase the contact time that that force is applied, you can also increase the change in velocity. So how do you increase the contact time? Well, that's what happens when you follow through. When you follow through, the club is in contact with the ball for just a little bit longer, imparting more force and resulting in a bigger change in velocity and therefore a larger hit. All the conceptual examples that we've talked all the conceptual examples we've talked about to this point have led us to this equation that we have here. It's called the impulse momentum equation or the impulse momentum theory. And what we have is we have this term J right here. And J is called impulse. And oftentimes you'll also see J referred to as delta P because really what impulse is it's defined as the change in momentum. So impulse, or J, can be calculated in two separate ways. And the first one is by taking the force and multiplying it by the contact time. Okay, both of those things will result in what we call the impulse. The second way we can do it is we can do it by the change in momentum, which is the mass times the change in velocity. So this doesn't really introduce any new variables with the exception of impulse. So when we say impulse, this variable should not be is J, but can also be expressed as delta P. You want to make sure you want to add that in there. And it's defined as the change in momentum, and there are actually two different ways of expressing the units. Now, more commonly, you will see Newton seconds as the expression for impulse, but really, a Newton second is the same thing as a kilogram meter per second squared. Because if you think about it, if you're talking about the change in momentum, that's the final momentum minus the initial momentum. That right there has to be the same units, otherwise you couldn't subtract them. So as a result, you kind of have these two units that could work either way for impulse, but this Newton seconds, that tends to be the one we use when we're talking about impulse. Force is the same, time is the same, mass is the same, change in velocity is the same. All of those values are the same, but you do need to know how to work this equation. So if I give you force, mass, and change in velocity, you can solve for time. If I give you mass and change in velocity, you can solve for impulse. There's lots of different variations on this particular equation that you need to become familiar with. So the first one says a ping pong ball launcher is launched on a frictionless surface. The ping pong ball launcher is capable of firing a 2.7-gram ball. This projectile is fired from a rest position at 24 meters per second when hit by a firing pin with a contact time of 4 milliseconds. What is the force exerted on the ping pong ball launcher? So we take a look at all our numbers. We're going to underline all our numbers that are there. and we're going to assign them variables. And so the first thing that we want to realize is that it's fired from a rest position, so we can say our initial velocity is 0. We know that it comes to 24 meters per second, so we can say our final velocity is 24 meters per second. Okay, we also have the mass of the ball as 2.7 grams, or 0.0027 kilograms. You should be able to convert to kilograms. Next, you have the contact time, and the contact time is 4 milliseconds, or 0.004 seconds. So if you look, there were two different conversions that we had to do in this case. Now this question says, what is the force exerted on the ping pong ball by the launcher? Okay, so we're trying to solve for force, and we're going to use our impulse momentum equation. J equals F delta T M delta V. So if you look right here, I can use any variations of these formulas. If you look, I have some sort of information that would give me change in velocity. I have some sort of information that gives me mass. I have some sort of information that gives me time. And what I'm trying to solve for is F in this case. So the two parts of the equation that I want to use are these two. I don't want to solve for J at all. I'm not interested in what the final value of the impulse is, nor do I have the impulse. So because of that, I'm going to use the equation F delta T equals M delta V. So trying to solve for force, that's what I'm looking for. So it's a F times 0.004 equals 0.0027 times the change in velocity. Now remember, the change in velocity represents the final minus the initial. So in our case, 24 minus 0, which is 24. Well, at this point, you would divide both sides by 0.004 to get F by itself. And when you do that, you get times 24 divided by 0.004 gives you a value of 16.2 newtons. Just to let you know, knowing Newton's third law, this says what force is exerted on the ping pong ball is 16.2 newtons. What force is exerted on the ping pong ball launcher? Remember, Newton's third law says for every force there's an equal and opposite force. So if we're saying the ping pong ball is exerted at 16.2 newtons this way, what we have to say is the force on the ping pong ball launcher is 16.2 newtons in the opposite direction. So really it should be 16.2 newtons backward, or you can say negative, or you can say left, but it's got to have some sort of indication that it's in the opposite direction. The next one says you have a 0.4 kilogram super ball that is dropped from a height of 25 meters, rebounding to a height of 20 meters. It says a force sensor on the ground records the average force during the collision to be 280 newtons. How long was the ball in contact with the ground? So you have the mass of the super ball, which is 0.4 kilograms. You're given the heights, and those heights right there are going to be important because we're going to have to figure out the velocities, or the velocity change of this particular ball. So you're also given the force is 280 newtons, and you know that we are trying to solve for the contact time. That's what we're looking for. So the equation that I'm going to use is the same F delta T equals M delta V. The problem is that I have M, I have F, and I'm trying to solve for T, but in order to get to T, I need to figure out what the change in velocity will be. So in order to do that, I can use either your energy equations, or you can use kinematics, whichever one you're more comfortable with. They're the same. So whenever you do this, you can go ahead and solve. I can say, okay, this thing right here has gravitational potential energy, and when it hits the ground, it has kinetic energy. So I can say mgh equals 1/2 mv squared. The mass of it cancels out for now, and we would say 9.8 times 25 is equal to 1/2 v squared. So whenever you multiply that out, you get 9.8 times 50, and then you would take the square root of that value, and when you do that, you get, no, that's not it. You would take 9.8 times 50, and you would take the square root of that value, and you would get 22.13. So just before the ball strikes the surface, it has a velocity of, in this case, it would be negative 22.13 meters per second. People say, but wait a second, the calculator didn't tell me negative, it told me 22.13. Remember, when you take the square root like we did to solve for the velocity, you have to get a plus or minus solution. Since the ball is moving down, it would be a negative solution, or minus 22.13. We need to do the exact same thing for the ball when it's on its way up. Now, we can do the same thing. Mass gravity height is 1/2 mv squared, or 9.8 times, in our case, 20 equals 1/2 v squared. When we do it that way, you would get 9.8 times 40, and you take the square root of that value, and you get 19.80. So that right there is a positive value. And people say, wait a second, we just did a negative value. Remember, the height of 20 meters that it goes to, it's moving up that direction. So the ball is moving a positive 19.8 meters per second as it moves up to a height of 20 meters. So now we have our change in velocity. We have an initial velocity of negative 22.13, and we have a final velocity of positive 19.80. So that right there is going to go ahead and tell us what our change in velocity is going to be. So if you take 22.13, excuse me, we've got to take our final velocity, which is this, and we have to subtract our initial velocity, which is that. So 19.8 minus, or excuse me, minus a negative, which is plus a positive, 22.13, you have a change in velocity of 41.93. Okay, now that I have my change in velocity, I can now plug into my equation that I've been waiting to use, which is this F delta T equals M delta V. So, I have an average force of 280 newtons. I'm trying to solve for the time. It equals 0.4 times the change in velocity, which I calculated to be 41.93. Multiply all those out, divide by 280, and you end up getting 0.06. Time is 0.06 seconds. So the ball is actually in contact with it for a very, very small amount of time. Now, with a regular Super Ball, it's going to be in contact for a lot longer, so it's not going to have as great of a force. But that kind of gives you an indication of what we're talking about. Now, two things that are really important here is the fact that we changed the direction, so our velocity changed. When our velocity changed, we had a much, much bigger change in velocity according to our force equation. If we hadn't been real careful with our positives and negatives, we would have had a much, much, much smaller change in velocity, and our answer would have been very, very different, very, very wrong. So make sure that you're paying attention to the direction when you're looking at change in momentum questions. It's pretty tough, so if you did not use trig whenever you were talking about projectile motions, and I mean sines and cosines, you might want to skip this one and kind of talk to your teacher about it a little bit later, but let's go ahead and go through it. It says that in order to hit a baseball over a fence, a player must hit it at 38.7 meters per second. So let's go ahead and draw that out. 38.7 meters per second, and it has to do it at a 45-degree angle, which means that there are components to the velocity. Because it's a 45-degree angle, it's going to have to be 27.4 meters per second up and 27.4 meters per second to the left, or excuse me, to the right. Now, how is this going to be particularly important? Well, you're not going to be able to figure out the change in velocity until you look at the individual components. Momentum is exerted in a one-dimensional component. So you look at momentum in the x direction, or you look at momentum in the y direction, but not in both, just like we did with velocity. So what I'm going to do now is I'm going to draw the ball coming in. So the ball is initially coming horizontally at a velocity of 40 meters per second. And what I need to do is I need to change the velocity of the ball from a kind of a negative 40 to a positive 27.4 meters per second. So the change in velocity in the x direction is going to be 67.4 meters per second. So if you look, I'm going from 40 this way to 27.4 that way. But that's the change in velocity in the x direction. There also has to be a change in velocity in the y direction. Now, we're going to assume that the ball was traveling horizontally when it was struck. So because of that, we can say, all right, well, that means that the change in velocity in the y direction is 27.4 meters per second. So this right here represents our change in velocity. And you say, well, but there's an x and a y. And you're right, there is an x and a y. So what we need to do is we need to say, okay, if there's going to be an x and a y, we can put those things together using a triangle. So now we can say I have 67.4 meters per second here. I have 27.4 meters per second there. And I can put them together using the Pythagorean theorem, where a squared plus b squared equals c squared. Or what I can do is I can say that plus 67.4 squared equals about 5,300 whenever you add those together. You take the square root of both sides and you end up with a velocity of about 72.7, we'll call it 72.7 meters per second. That represents the total change in velocity. So this right here is the total change in velocity. Now, if we're trying to figure out the force that the ball is struck with, we can use our equation F delta T equals M delta V. I have my delta V is going to be 72.7. We have the mass of a baseball that we've talked about before is about 0.144. It should really be listed, but we've used it in other examples as 0.14. The change in velocity is 72.7 meters per second, and so yeah, the 0.14 should be listed in the problem, but it was something we had used before, so that's why it wasn't repeated. So you have 0.14 times 72.7, and then on the other side you're going to have the force, which is what you're trying to solve for, and then you have the 7 milliseconds of contact time, so it's 0.007. So you're going to take 0.14, you're going to multiply it by 72.7, and you're going to divide it by 0.007. And when you do that, you end up with a force value. It's a really, really, really large force value of 1,454 newtons. Okay, it's a pretty big force value for hitting a baseball. The next example is example B4, and it says calculate the impulse of the object in the first 10 seconds based on the graph below. Now remember, you have the equation J equals F delta T equals M delta V. Now in this particular case, if you were to read this, and it's kind of tough to read, this is a force time graph. If you have a force time graph, that means that this is the part of the equation you're looking at. So whenever you take two variables and you're multiplying them together, what you're really trying to do is trying to solve for the area under the graph. Now I can't just take the force, like the force here, and the time here, and just multiply them and get the impulse value, because the force was not the same for the whole time. I'd be including this whole part, which is not there. So because of that, what I need to do is I need to solve for the area under the curve. In this particular case, all the way through to 10 seconds. So I need to find the area of this shape right here. People say, well, that's kind of an irregular shape. I don't know how to find the area of it. Well, it's okay. What you can do is you can actually divide it into two familiar shapes. So I have this shape right here, which is the shape of a triangle, and I have this shape right here, which is the shape of a square. Square is the easiest one to do. So we'll find the area of a square. It's just base times height. And if you look, this right here is where the square starts. So it has a base of 5. And if we look on the side, we can see it has a height of 20. So the total area of the square is 100. And then if we look at the triangle has a base of 5. It has a height of 20, just like the square. But because of the difference in the formulas, the area of the triangle is going to be 50. So when I'm looking at the total impulse in this case would be 150 newton seconds. Not just, you can't just multiply them. If you just multiplied them out, it would be 20 times 10 and you'd get 200. That's not the case. Please make sure that whenever you're looking at a graph, that you're looking at the area under the curve in order to figure out what the impulse is. In this last example, it says you have a 5,000 kilogram Mack truck that's initially at rest at an intersection. So we have a mass and we have at rest. And it says when the light turns green, the engine pushes the car with a force of 100 newtons for 24 seconds. What is the final velocity of the truck? So we have the mass is 5,000. We have the initial velocity is 0. We have the force exerted on the car is 100 newtons. And we have the time is 24 seconds. So I can now use my F delta T equals M delta V. And I can go ahead and solve. I would say, okay, 100 times 24 equals 5,000 delta V. And I would say, okay, 24 times 100 would be 2,400. Divide by 5,000, and you end up with a delta V of 0.48 meters per second. Remember, delta V is equal to final minus initial. In this case, it's not going to matter because our initial velocity is 0, which makes our delta V the same as our change in velocity. But this is a step that you can't leave out because the initial velocity is not